Welcome back to the deep dive. Today, we're doing a deep dive that, and I'm not exaggerating here, might fundamentally challenge what you think you know about the physical world, specifically what you are actually made of.
Yeah, we're going way past the high school textbook
Yeah.
stuff. Atoms, electrons, all that. We've got a stack of research here from particle physics that gives us a real shortcut to understanding mass itself. And we're focusing on, well, the most common building block there is, the proton.
And it is mind-bending. For decades, we've all pictured matter as this solid, reliable, stable thing, but the research we've pulled shows that the proton, the very core of every atom in your body is. It's anything but a solid little ball. It's this incredibly dynamic, high-energy place.
Exactly. Our mission today is really to unpack the secret life of this particle.
Yeah.
We want to reveal the physics behind the proton structure, which is just,
Hmm.
it's so much more dramatic and a lot less material than almost anyone thinks.
The first shockwave from this research, for me, was just the scale. We all know atoms are tiny, but the sources confirm that the things that build the protons, that then build you, are themselves built from things thousands of times smaller. It's components of components.
Right. We're going deeper than the nucleus. We're looking inside that nucleus at the particles that make it up. And what we find inside the proton, these tiny creatures called quarks, they are responsible for holding together, well, essentially all known matter.
It's genuinely hard to wrap your head around that. You look down at your hand and you just assume it's this stable thing made of atoms. But inside every single one of those atoms, in the nucleus, something chaotic is going on. So, okay, let's start with the recipe. What's a proton made of?
If we peel back that simple picture of a solid ball, we find the proton is made from a surprisingly small crew, just three quarks. Two up quarks and one down quark, to be specific.
Three tiny pieces. That's it. Now, if the proton is the building block of our mass, the logical thought, the classical assumption, is that those three particles must make up almost all of the proton's weight. They're the stuff, so they have to be the mass.
And that is the exact assumption that this research just shatters. This is the core revelation. If you add up the mass of those three quarks, their theoretical rest mass, they account for less than 2% of the proton's total mass.
Wait, stop right there. Less than 2%. That is it's astonishing. When you weigh yourself, 98% of that weight isn't accounted for by the actual physical particles you're made of. It just begs the question, right? If the quarks are only 2%, what on earth is the other 98%?
This is the 98% secret. And the sources are, they're completely clear on this. The rest of the mass is not solid material. It's described as, and this is a great phrase, energy, force, fields, and nuclear glue.
Nuclear glue. I love that. It's such a vivid term for something so profound. This completely changes the definition of mass for you, for everyone listening. You're not primarily made of stuff. You're overwhelmingly a collection of dense, tightly controlled energy and force fields.
And that energy, that 98%, it's all needed just to keep those tiny 2% pieces from flying apart. Without it, there's no proton, no atoms, no us.
Okay, so we have three quarks rattling around in there, and they need this huge reserve of energy just to stick together. Let's get into that mechanism. What is this nuclear glue?
This is where we meet the strong nuclear force, or just the strong force. It's the binding mechanism that generates that 98%. And it isn't just strong, the sources confirm it's, without a doubt, the strongest fundamental force we know of. It completely overpowers gravity and electromagnetism at this tiny scale.
And we have to put that in context because electromagnetism is already incredibly powerful, isn't it?
Yeah.
The two up quarks and the proton, they're both positively charged, so they should be repelling each other with immense force. The strong force has to beat that.
Precisely. If you only had electromagnetism in there, the proton would explode instantly. The strong force is what holds it all together against that intense pressure, and it only works over these incredibly short distances, the diameter of the proton itself.
So how does it work? Is it just a field? The sources use that great analogy of nuclear glue.
And that analogy is actually really good because the strong force uses these little messenger particles called gluons to transmit its power. The name comes right from the word glue. They basically mediate the interaction that binds the quarks.
I love that idea of force carriers. It's not just a static field of energy. It's an active, constant exchange. I remember one of the sources painted this image. It's like two people trying to stay close together by just rapidly throwing this heavy medicine ball back and forth. The momentum of the exchange is what locks them in place.
That's a great way to visualize it. And in the proton, this exchange of gluons is happening so fast and so intensely that it creates this incredibly powerful bond. That's the glue.
Yeah, and the sources had a bit of fun with it, describing the quarks and gluons almost like creatures from some kind of, I don't know, a strategy game, which helps make it memorable. But behind that fun language is the incredible fact that this little game is creating almost all the mass in the universe.
It is the foundation. Without this intense gluon-mediated dance, you get no stable protons, no atomic nuclei, and therefore no physical world.
Okay, let's shift from the how to the where. We've got the strong force working like crazy, driven by gluons, holding these quarks together. So let's just destroy that image we all have in our heads, the little, stable, hard sphere.
Oh, that image is completely wrong based on this, yeah. If you think about the enormous energy needed, that missing 98%, the proton can't possibly be a calm, solid object. That much energy in one tiny space means one thing: chaos.
Absolutely. The sources describe the inside of a proton as dynamic, chaotic, and incredibly crowded. It's better to think of it not as a ball, but as a high-energy vortex of energy. You have to imagine this tiny space where kinetic and field energy are just completely dominant.
And this vortex is driven by things moving at, speeds approaching the absolute limit of the universe.
That's the detail that really stuck with me. The quarks aren't just sitting there, they are constantly zipping around inside the proton at relativistic speeds. We're talking close to the speed of light. And at the same time, gluons are just constantly being exchanged at blinding speed to keep that bond.
And here's the kicker. The chaotic activity is the mass. It's the kinetic energy from those superfast quarks, plus the field energy from the gluon exchange, that adds up to that 98% of the proton's mass.
Right, so if you're listening and asking, how can movement equal mass? That's the central idea of this whole deep dive. The speed is so high, the energy is so concentrated that we perceive it, we measure it as mass.
Exactly. We have to come back to Einstein. E equals mc energy 1. Mass and energy are two sides of the same coin. When we put a proton on a scale, so to speak, what we're actually measuring is the total energy locked inside that tiny confined space. The stuff of the quarks is almost nothing. It's the energy of the system that has weight.
So this is the synthesis. Let's zoom out and look at the big conclusion this research forces on us. If the proton is 98% trapped energy, what does that mean for, well, for everything, for the entire physical universe?
It means that the mass we see around us, your body, this planet, the stars, everything you think of as solid, is in fact overwhelmingly trapped energy. It's not a solid substance in the way we normally think about it.
And that brings us right back to E equals mc squared. We all know the equation, but this research shows you just how fundamental it is to your own existence. The vast majority of the m, the mass, in matter comes directly from the E, the energy, and the ratio isn't close. It's 98 to 2.
It's this beautiful, almost poetic irony that the sources point out. The smallest things we know of, quarks, gluons, the strong force, are responsible for generating and holding together the largest things in the universe. All of it. All physical structure.
I want to just sit with the philosophical impact of that for a second. The real aha moment for anyone listening is that your own body is basically a very, very tightly regulated energy field. It's governed by a force that is orders of magnitude stronger than anything we can imagine. The stability we feel is, well, it's an illusion.
A beautiful illusion, maintained by constant near-light speed activity. The sources even note how small our own minds feel when you're faced with the sheer power it takes just to hold one of these things together. We see stability, but the reality is pure contained energy.
Yeah, it forces you to completely reevaluate what it even means to be solid or material. Solid is just energy moving really, really fast, stuck in a very tiny box.
It really is. So if someone asks you what you're made of, the most accurate answer is mostly force.
Okay, before we leave you with a final thought, let's do a quick recap of the core insights from this incredible deep dive.
First, the building block of matter, the proton, is made of just 3 quarks.
Second, and this is the big one, only a tiny fraction less than 2% of a proton's mass actually comes from those quarks. The other 98% is pure dynamic energy, fueled by the strong force.
And finally, what that means is that the mass of every physical thing in the universe is overwhelmingly just trapped energy. It's a stunning, real-world proof of EMCNA.
It's an amazing realization that the entire structure of reality hangs by the thread of the strongest force in existence. But we want to leave you with one final provocative thought from this material. Something to chew on.
So consider the immense energy density we've been talking about, the energy it takes just to keep one single proton stable. If the tiniest things in the universe, the quarks and gluons inside that proton, are performing more work than all of humanity's factories combined, just by existing,
Yeah.
what does that imply about the untapped energy potential sitting inside what we think of as ordinary matter?
Just think about the sheer number of protons in the universe, all holding that 98% secret. It really makes you look at every single object, a rock, a cup of water, your own hand, in a completely new and kind of electric way. Thanks for joining us for this deep dive into the building blocks of reality. Until next time, keep exploring.